Okay, so before we get started in our conversation, I just kind of wanted to touch base with you guys about what this wrap up kind of looks like. We're going to go ahead and finish up the lecture side of things this evening, and then I will also put out everything that you need to have accomplished between now and that final date of class. I know that with everything switching to online, you guys have a lot of things on your plate, managing things in a different way than what you were initially anticipating. And so I just want to make sure that you guys have a nice big window to be able to sit down and kind of wrap things up for this particular class. So like I said, I'm going to finish up the lecture side of things with this particular lecture, and then you will have an assignment for this week, and then you will have what would be the equivalent of your final. And I will get that all out to you guys so that you have between now and that last date that class would have met to get that all taken care of. So please just make sure that you guys are watching those dates and making sure that you get everything turned in prior to that final date of class, because I then need to get grades put in, grades figured, and grades sent off to the college shortly after that final meeting date. So if you have any questions between now and then, please send those to me. I will get those taken care of for you. But this will be the final lecture that we have. And then you will have two assignments, one that goes along with this lecture, and then one that is going to be as much of a final exam as we can do. Okay. So you guys will be getting a new packet, and the packet that you guys are going to be receiving is going to be over the final information that we need to go over with the nervous system. So our last conversation really took some time to go through the parts of the nerve. And one of the biggest things with the nerve is to understand that it's a little bit different than your other cells because the job that it has to do is much different. We are not worried about the nerve cell taking care so much of the inside of the cell, but we are looking at something now that is trying to take information from one location and get it to a second location. And because of that job or that function, you have this nice long narrow cell that is your nerve cell. So that job can be taken care of. Now, your nerves are going to take information from the brain and from the spinal cord and then extend that out to all the parts of your body. So, when we look at the final two parts of our nervous system, looking at the spinal cord, looking at the brain, now we're getting into the central core of your nervous system and where the decisions are made, where processing happens, and now we're getting into the higher level function. So, kind of working our way up, we started with the nerves. Now we're going to go to the spinal cord, and we are ultimately going to end with the most important part, which is the brain. So, looking at the spinal cord, that first slide that you have there, a couple of things just to note right off the bat. So, you can see the brain on top, you can see the spinal cord, and then the picture that you have on the right is the spinal cord itself. No bone protection, no vertebrae around it. The brain is no longer attached at that point. So the image that you have on the left-hand side is showing you everything, the brain, the spinal cord, along with the bones that protect it. And the image that you have on the right is just what the spinal cord would look like by itself. Now, with the spinal cord, some of the things that we have, you see the brain stem right at the top, and that's going to be part of the transition point from the brain itself down into the spinal cord. And we'll get more into that a little bit later on. As you move down the spinal cord for the most part is going to be about the size of your pinky finger. And so if you just take a quick look at what your pinky finger looks like, that's going to be about the diameter of your spinal cord from top to bottom. Now, of course, there's always going to be a few exceptions. And so you'll see at two places on your spinal cord, you have what are called enlargements. You have one in the cervical location and you also have one in the lumbar region. Now, in those two places, you will have a little bit more of a bulge within the spinal cord. And the reason for that is that both of those places, that is going to be a spot where you are going to have extra nerves because those nerves are going to branch off. And those are going to be the nerves that run down your arm all the way to your fingertips in the cervical area. And then when you get down to the lumbar area, that extra kind of bump that you have there is going to be all of the nerves that are going to branch off and extend down your legs all the way to your toes. So that is the reason why you have a little bit more mass in those two places, because those nerves have to extend further away from the spinal cord to make sure that you have that nerve sensation all the way down to your fingers, all the way down to your toes. Now, some of the other structures that you see there, and if you will look at the image on the left-hand side, we already talked about the enlargements, but if you look at the very last one, the cauda equina on the left-hand image, if you translate that, again, because a lot of our terminology from anatomy comes from Latin and Greek roots, and this is one of those places. So cauda equina means horse's tail. And at this location, we're in the lumbar vertebrae. This is the place where the spinal cord is actually going to start to fray. And it turns into individual little strands instead of being kind of all bundled together. And because of that fraying and the individual strands that you get at that point in the spinal cord, it looks like a horse's tail. And that's where the name cauda equina comes from. Now, if you go back over to the right-hand image, it talks about the filum terminale. Now, this is going to be the end of the spinal cord. So the cauda equina, you're starting to get that frayed appearance, the individual strands. At the filum terminale, what's actually going to happen is now the spinal cord is going to start to taper and become very narrow. This is going to be about the point where it's going to start making its move and transitioning down into the sacrum and down from there. And you can kind of see that as you compare those two pictures side by side. But now we have a narrowing of the spinal cord as it gets into those final parts of the vertebral column. The next image that you guys have talks about the Meningeal layers. The Meningeal layers are going to be 3 layers of connective tissue that you have. And these are both on the spinal cord and around the brain. So I know this particular image, the inset picture there, shows you a little bit more around the brain, but these would also extend down and be in the same layering pattern when you get around the spinal cord as well. Now, what these connective tissue layers actually do is they're going to help anchor and hold these structures in place. So the brain, even though it doesn't have a whole lot of excess room, does have a little bit of space between the skull itself and the brain. And just to kind of help anchor and hold the brain to make sure that it doesn't shift too much and start bumping into the sides of the skull, the Meningeal layers will help hold it in place. The other big thing that the Meningeal layers will do is they will help hold the cerebral spinal fluid around these two structures. Now, cerebral spinal fluid is very important because this is really where the nourishing material for your central nervous system is going to come from. The ions that you need, other materials, nutrition that you need to be brought to the brain and the spinal cord, it's going to be the job of those Meningeal layers that once that cerebral spinal fluid is there, they hold it in place up to those two structures. So the 3 layers, you have the dura mater, the arachnoid mater, and the pia mater. So the dura mater, its name translates into tough mother, and that is going to be the outermost layer. So this would be the layer that you would find closest to the skull. Now, just underneath that, you are going to have the arachnoid mater. And arachnoid, most of us, when we hear arachnoid, we kind of associate that with spider, arachnids. And that is very true in the naming of the arachnoid layer. It is not continuous. It's not a continuous sheet. It actually has holes in it. And this is because it is the middle layer. So it's underneath the dura mater, it's above the pia mater, so it's sandwiched in between. And so material can move through the arachnoid mater. It has holes and gaps in it to allow for that cerebral spinal fluid to kind of flow back and forth. And so if you were to look at it by itself, it would have very much a web-like appearance, and that's where the name arachnoid mater actually comes from. The final layer is the pia mater. The pia mater is going to be closest to the actual structure. So if it's a meningeal layer in the brain, this is going to be the layer that would actually touch the brain. If it's a meningeal layer within the spinal cord region, it would be the layer that actually touches the spinal cord. Now, not only does it touch the spinal cord or touch the brain, It actually follows the grooves and formations of the brain and the spinal cord. So if the brain dips, the pia mater will dip also. If there's a high point or a peak, then the meningeal layer will follow that. So it is a layer that follows right to the grooves and any formations that you have on the brain or on the spinal cord. The next slide that you guys have talks about the cerebral spinal fluid. Now, cerebral spinal fluid is not something that we have in an abundance because it is placed in areas where we have very limited space available. So this is going to be between the brain and the skull, or between the spinal cord and the vertebrae. So not a lot of space. And what the cerebral spinal fluid will do is it's actually going to circulate through these structures and through this area, like I said, to make sure that any of the nutrition that needs to be delivered to these two parts, the ion concentrations that need to be maintained so that they can fire nerve impulses, all of that is going to be taken care of by the CSF, that cerebral spinal fluid. Now, with the CSF, it's about 120 mils. And if we were still in class, one of the things that I would have you guys do is actually measure this out. So I bring beakers in, you guys would measure out what 120 mils look like. And just to kind of put a visual behind it, because 120 mils is not a whole lot of liquid, especially when you are talking about two of the most important structures that we have within the human body. Now, the other thing with the cerebral spinal fluid is because it is constantly surrounding the brain and the spinal cord, it's very important that it does not become dirty. It doesn't become filled up with all this waste product. And so if you think of your bathtub, if you have multiple people that are going to take a bath or a shower at your house, you have water coming in, you have the drain taking the dirty water out so that people are not having to bathe and use the same water over and over again. And within the central nervous system, you have the same sort of setup. You don't want that same cerebral spinal fluid flushing through the system over and over and over again, because eventually it is going to become dirty. It's going to need to be replaced. And so within the central nervous system, you have a couple of structures that are going to help take care of that. You're going to have structures that are going to bring in new cerebral spinal fluid, and then you have structures that are going to take that fluid out. So one of the most important structures that we have here is the choroid plexus. That is top line of your information there. And that is where the cerebral spinal fluid is going to come in. So if you think about your shower head or the faucet that actually brings water in, that would be the equivalent of your choroid plexus. And then you have these arachnoid villi. They are the equivalent of the drain. So they are going to drain out old CSF so that it doesn't build up too much fluid, but you can keep clean fluid in and around the brain and the spinal cord. The next slide that you guys have is a cross section of the spinal cord itself. And so what they've done is they've cut a section of the spinal cord and you are now looking down on top of it. So the biggest thing with the spinal cord is we always talk about the spinal cord, and if you are thinking that somebody might have a spinal cord injury, that you don't move them too much because you don't want to cut through the spinal cord. Remember, this is the link between the brain and the nerves of your body. So this is how information is going to be transmitted from the brain out to the nerves so that you guys can feel sensations. You can get that information from the brain. If you cut the spinal cord, you now cut the link to those nerves of the body. So it's very, very important that the spinal cord is maintained and kept intact. And if you do suspect that somebody has a spinal cord injury, you try to move them as little as possible. Because remember, with the spinal cord itself, this typically would be surrounded by vertebrae. And in this particular picture, they don't have the vertebrae on here. But if you think about those vertebrae, they are bones. They have a very irregular shape to them. And if you break those vertebrae, you get a lot of very small, sharp pieces of bone right next to the spinal cord, which is about the consistency of cooked spaghetti. And if you think about how much effort it takes, if you have a piece of spaghetti and you try and cut it with a fork, that it's not a lot of resistance. So now you take these broken vertebrae that are potentially around the spinal cord and you start moving them around. It's basically like little knives that are cutting into that spinal cord, and it doesn't take a whole lot to cut through it. Once you sever the spinal cord, anything below where that cut happened is now going to be unable to receive information from the brain. So it is very important that the health of the spinal cord is maintained. If there is a threat or a possibility that any damage has been done to the bones around the spinal cord, that, like I said, you don't move them unless you absolutely have to. Now, with the spinal cord, one of the interesting things I think with the structure of it is that on its own, it's almost divided into two independent pieces. So if you'll start out by finding the posterior median sulcus and the anterior median fissure. Sulcus and fissure are terms that indicate a kind of cut in something, a natural cut. It's supposed to be there. But with these two structures, if you find them and one is on the top side, one is on the bottom side, you'll notice that if you follow those in, they almost cut the spinal cord into left and right halves on their own. So basically you have these two bundles of the spinal cord that are stuck together, and there is a very, very fine strip that is linking those two sides together right at the core. So naturally, the spinal cord is already, like I said, in those two bundles. Now from there, you have some divisions of color. And you'll notice on the slide that you have some lighter colored areas within the spinal cord and you have some darker color areas. Now, the lighter colored areas are referred to as white matter. Those would be the sections of the spinal cord that actually have myelin. So with that myelin covering, they look lighter in color. We call them white matter. And within the white matter, we have areas that are known as the funiculi. So the lateral funiculus, you have the excuse me, the posterior funiculus and the anterior funiculus. So they're kind of around that outer edge. You can find them. But the funiculus is simply telling you areas where you have bundles of white matter. So you have one on each side, you have one on the front and one on the back. So those areas where you have large collections of white matter, we refer to those as a funiculus. So white matter and funiculus, those two terms are linked together. On the flip side, you have the gray matter. The gray matter, you'll notice, is all centrally located, kind of looks like a butterfly right at the middle of the spinal cord. And the term horn is going to be tied to gray matter. Gray matter lacks the myelin sheath. And so because you don't have that fatty covering, you get a darker appearance to those nerve cells. And that's why we call it gray. You have the anterior horn, you have the posterior horn, and it's just indicating that those are going to be sections or clusters of gray matter within the spinal cord. So white matter goes with funiculus, gray matter goes with horn. The next couple of slides you have talk about reflexes. Now, reflexes are something that are automatic responses to a particular stimulus. So it's not something that you have to learn. It is something that you are born with. And reflexes are really important to our survival because there are some things that you have to know how to do before anybody would be able to teach you. Sucking reflex, for example. You have a newborn, they need to immediately know how to use that sucking reflex so they can nurse or they can drink from a bottle, and they don't have the ability to learn that. There's no way to communicate that to them. They just need to know how to do it. So that would be considered a reflex, something that they just naturally have ingrained in them. They know how to do from the start. The startle reflex. Startle reflex, if you've been around little guys, they're sleeping and something loud happens around them, they will throw their hands up in the air. And even though they're still sleeping, they kind of look like they're cheering because their hands are up over their head, kind of like you would do if you were going on a roller coaster ride. And that's just another ingrained reflex that they have. Some people believe that it's actually their way of putting themselves in a good position to be caught. So in their minds, they're falling or something's happening to them, and so they throw their hands up to make it easier to catch them. That is a theory. They have no way to prove that beyond a shadow of a doubt. It's just one of the ideas out there. So a reflex is anything that, like I said, you automatically have, you know how to do, and it is going to be your natural response to a particular stimulus. So you would have sensory information come in, brain would process that information, and then your muscles or your endocrine glands are going to then carry that out. Now, if you go on to the next slide, this is going to be your visual that goes with that previous slide. So if you are more of a visual learner, this slide is for you, but it is the exact same information that was in the slide we just left. So in this particular case, you see the receptors embedded in the skin. Some sort of stimuli comes into that receptor, and we're going to send that to the nerve. And so you see that sensory information coming into the nerve. It's going to then move through the spinal cord. It gets processed, and within the spinal cord will figure out a way to deal with that sensory information. And then if you notice, it just loops that information right back out. So it doesn't go to the brain. It simply processes the information, sends the response back out, and you see that response then being sent to the muscle. The muscle will now contract or do whatever it's told in response to that information coming from your spinal cord. The next two slides that you guys have, and I want you to kind of look at these simultaneously. Now, it gives you specific types of ascending tracts and descending tracts. You do not need to learn those, and you don't need to be able to identify their location. But the reason that I include the ascending and the descending tracts is to kind of give you a little bit better idea of how the brain and the spinal cord work. So ascending tracts are going to be those tracts that are going to take information up to the brain, and descending tracts are going to be those bundles of nerves that bring information down from the brain or the spinal cord, depending on how far up it goes. Now, the reason that it's important that we have ascending and descending tracts within the brain and the spinal cord is because you don't want there to be a traffic jam. So if you have sensory information coming in and it's being relayed to the brain and the spinal cord, and you also have information coming out of the brain or the spinal cord at the same time, they can't run into each other. So you can't have information trying to come in and information heading out at the same time. So by having tracks that only go in one direction, it is going to ensure that you don't have that traffic jam. So they are kind of like elevators, but they only go in one direction. So ascending tracts are going to take sensory information to the spinal cord or to the brain. Descending tracts are going to take the response back out. So they are going to take whatever information that brain or that spinal cord has come up with, and they are going to relay that information back out so that the appropriate body part knows how to respond. But there are specific areas in your brain and your spinal cord, and they only work in one direction just to make sure that you don't get bogged down. The last slide, couple of slides that we have there on the nerves, first one talks about the peripheral nerves, and we had kind of talked about this last time also. Your peripheral nerves are going to stem from one of two places, either your brain or from your spinal cord. So if a nerve comes off of your brain, it's called a cranial nerve. And if the nerve comes off your spinal cord and then goes out to part of your body, it's called a spinal nerve. So that last slide that you have there that talks about the spinal cord is simply going to show those spinal nerves. So you have a total of 31 pairs of spinal nerves, and 8 are going to belong to the cervical group, 12 to the thoracic, 5 to the lumbar, 5 to the sacral, and 1 to the coccygeal. Now, for the number of cranial nerves that you have, I want to talk about that very quickly. You had 7 cervical bones, so there were 7 cervical vertebrae, but you'll notice that there's 8 cervical nerves. And the reason for that is because even though there's only 7 cervical bones, one nerve actually branches out above the top of your first vertebrae. So you have a nerve that comes out on top of C1 as well as underneath C1. And that's why we have what looks like an extra nerve. Even though there's 7 bones, we get 8 nerves associated with it. For thoracic and lumbar, it's an equal match. We had 12 thoracic vertebrae and we have 12 thoracic nerves because they branch out at each thoracic vertebrae. Likewise with our lumbars, 5 lumbar vertebrae, 5 lumbar nerves that are going to branch out and go to the different parts of the body. The only thing that I don't care for about this picture is that I wish they would have showed the nerves actually extending down the arm, because those nerves that come off of your spinal cord are going to go all the way down your arm, all the way down to the fingertips, and they would branch on both sides. So I realize they put the numbers there on the right hand side, but those nerves would come off both the right and the left hand side, going down to the ends of your extremities. So if you have somebody that has a spinal cord injury, depending on where that injury happens is then going to dictate how much of their body they have left to use. If you have somebody that has a cervical injury or a spinal cord injury, and let's say it happens between L1 and L2. So now that spinal cord is severed just underneath the first lumbar, just above the second lumbar vertebrae. So if you put your finger there, anything above that is still going to get information from the brain and will still function. You would still be able to control that. Anything below that point of your finger is now not going to get information from the brain, and you would lose control or use of that. If you would have a spinal cord injury at C1, C2, put your finger there. Now you can see how dramatically that is going to change the function of that particular person, because now anything below your finger, they are not getting information from the brain. It's not going to function. And anything above that, they would still have control of. So you can see how spinal cord injuries, depending on where it happens, that is going to really dictate how the person is going to be able to function afterwards. The next section gets into the brain. And the brain is going to obviously be in control of everything. Your higher level functioning, all of that is going to be taken care of within the brain. And as we go through this, we're going to talk about some of the major parts. So if you go ahead and find the parts of the brain, I'm actually going to start there. Just checking time. So with the parts of the brain, you have the skull, which is going to protect it. We already talked about the meningeal layers. The cerebrum, that is going to be the outer portion of the brain. It is the largest portion of the brain. So it is the outer covering that you have of the brain, and it is going to also be gray matter. So a little bit of a flip within the brain structure. In the spinal cord, the white matter was on the outside, gray matter was on the inside. In the brain, it's just the opposite. Gray matter is on the outside, white matter is on the inside. So that cerebrum is your gray matter. The diencephalon, that is the core region of the brain. So you see that right at the center. That is where two very important structures known as the hypothalamus and the thalamus are going to be located. Just underneath that, we have the brain stem. So within the brain stem, this is the beginning of our transition from the brain down into the spinal cord. And there's 3 parts within the brain stem. You have the midbrain, the pons, and the medulla oblongata. If you look over onto the other side, it talks about the gyrus or the gyri and the sulcus. Now, those are referring to the bumps and the peaks and valleys that you have on the surface of the brain. Surface of the brain is not smooth. You don't want it to be smooth. So the gyri are going to be the high points. The sulcus are going to be the low points. So when you get into those peaks and valleys of the brain structure, if it is the high point, we would refer to that as the gyri, and if it is the low point, it is the sulcus. Now, if you're talking about them all collectively, then it's referred to as a convolution. Now, underneath that, we have the corpus callosum. Corpus callosum is going to be the connection between the right and the left-hand side of the brain. So it's a kind of a curved section that you have right at the middle of the brain. You can see the arrow going to it there. That is going to be the only place. It's a bundle of nerves. A lot of places will refer to it as a bridge that connects the right side and the left side of the brain to each other so that there can be communication between the two halves of the brain. From there, we have the cerebellum. Cerebellum is at the back of the brain, and it is going to be the location where you have kind of control of your muscles, your posture, body awareness, so that you know where your body parts are in relationship to each other. Even if your eyes are closed, you know if you're sitting upright, if you're laying down, whatever the case might be. And then you have the spinal cord tucked just below that. From there, we have the brain ventricles. Now, with the brain ventricles, you have a total of 4. And this is going to be where the cerebral spinal fluid is going to get moved through the brain on the inside. So there are, like I said, a total of 4 of them. And the first ones that you have are referred to as number 1 and number 2. So you can call them the lateral ventricles, and you'll notice you have 1 in each side of the brain. So they get numbered 1 and 2, or they're known as the lateral ventricles. Then you have 3, or the third ventricle. So you'll notice that the lateral ventricles actually come together right at that central point. That's your third ventricle. And then as you move down towards the spinal cord, you get into the fourth ventricle. And that's how we're going to move that cerebral spinal fluid through the brain structure. The bottom image that you guys have just gives you a little bit different view of how that is all positioned. So you get the frontal view with the top picture, and you get a side view with that bottom picture. But just to kind of understand how that cerebral spinal fluid is going to move through. The next slide that you guys have shows you the lobes of the brain. And there are 4 major lobes that we have within the brain. You have the frontal lobe, you have the occipital lobe, and you have the temporal lobe as well as the occipital. So frontal, parietal, temporal, occipital. Those are your 4 lobes that you guys have. And I put a slide in there that shows you the main things that they do. So functions by lobe. The frontal lobe is going to be more responsible for your higher level functioning, your kind of cause and effect. If I do this, this would be the potential happening or outcome of that. But that's really going to take place within that frontal lobe. This is also the last lobe of the human brain to fully develop. Now, in females, that will happen late teens, early 20s. For guys, it's early 20s to mid 20s before that frontal lobe fully finishes off its development. Not a gender slam whatsoever. It is scientifically proven. Females, it just happens a little bit earlier. For guys, it's going to be into the early to mid 20s before that happens. Parietal lobe. Parietal lobe is going to deal with understanding when people talk. It's also going to be linked to being able to pick up on thoughts and other emotions that are tied to the words or expressions that somebody is using. Temporal lobes, because of where it's located, and if you look at that picture, temporal lobes are going to help with the process of hearing, which would make sense since it's right on point with where your ears are. And then it's also going to, on the sensory side of things, help with your visual images, making connections to music, and also being able to pick up on patterns within information that you're provided. And then the last one, the occipital lobe, actually happens on the back of the head. And this is going to tie to your vision. So with the eyes being on the front side, some people don't understand why the occipital lobe would be all the way in the back. It actually is so the nerves that come off the back of your eyes have time to process and put together the images. So they need that distance in order for that to be able to happen. If you ever get hit on the back of the head and you see stars, what's actually happening is those nerves within your occipital lobe are getting stimulated from whatever hit you in the back of the head. They have to do something with that stimulus, but because it came from the back of your head, there's no visual associated with it. You'll see those little color bursts, and that's actually what's happening. So the diencephalon, we talked about that at the beginning. The 2 structures that it has associated with it are the thalamus and the hypothalamus. Now, the thalamus is an important structure because what it actually does is as information comes into your brain, the thalamus is going to make sure that it gets sent to the appropriate location. So information is processed in different places of your brain. So you have a language part, you have a memory part, you have all these different locations where information is actually going to be processed. The thalamus is going to make sure that as that information comes up to your brain, it then gets directed to the right location so it can be processed in the appropriate way. The hypothalamus, easy way to remember it, hypothalamus and homeostasis, they both start with the letter H. So anything that deals with maintaining homeostasis is going to be in part the job of the hypothalamus. So your heart rate, maintaining your blood pressure at the appropriate level, body temperature, all of that is going to be linked to that hypothalamus. And then the last one that we have shows you the brainstem again, just a little bit different view with the brainstem. And you get the side view of it here. So you can see the midbrain, which is on top. Pons is going to be that little bulge kind of in the middle. And then you have the medulla oblongata. So within this section of the brain, or the brain stem, you are going to have some of your reflex centers. So your reflex center for breathing is going to be in this particular location. Heart rate is going to be in this location. Also, your ability to kind of link hearing and seeing something. So if you hear something and you'll kind of turn your head to look and process it, that is going to be embedded within that part of your brain as well. And so when you start to get into spinal cord injuries, because those reflex centers are located in that brainstem portion, you could have a very high spinal cord injury. We talked about C1, C2, and I had you guys take a look at what that would do to body function. But because those reflex centers are in that brainstem, that would actually be above that C1, C2 location. And so that's why you can have somebody with a very high spinal cord injury in which they would still be able to breathe. Might need assistance with that, but it's still above where that spinal cord injury actually took place. So that is our information for the brain and the spinal cord. I will be putting the rest of your information that you guys need into Blackboard so that you have it. If you have any questions, please let me know. And I hope you guys continue to do well, getting ready to move into our summer session.